Hello statistics student, this video is for chapter 4.3 Binomial Probability Distribution. Binomial probability model a random variable called binomial random variable, which is a special kind of discrete random variable that is looking at count of success. So it's in a very abstract way, it's looking at counting something. When you in the procedure, you're actually doing n trials. So let's look at some of the restriction or some of the requirement of being able to model x, which is a random number that is determined by chance, and x is a count of success. X is number of success in n trials. So in a procedure, you would have a fixed number of trials that maybe you will be tossing coin 10 times, or maybe you toss a coin 5 times, or maybe you're selecting 10 students, or you're selecting 10 poker chips. So you're always doing something repeatedly, and they're all you know a fixed number that you will end. And then the trials must be independent. They don't interfere with each other. The success of one does not interfere with the next trial. Each trial has exactly two outcomes, success and failures. So when you complete one trial, you look at the success. You look at if you get what a particular one that you're counting, and if it is a success, then you count one more. And X is the total number of success in n trials. And then the probability of success remains the same in all trials. So these are the four requirements. If in a very high level, X satisfy this four requirement, the P of X can be calculated by a common formula or by a common calculator function. There are a lot of binomial calculator that can find probability of that particular situation. I did not write down the example here, so I'm going to go to another page to talk about some of the examples that can be modeled by binomial distribution. And in every cases, we'll look at the four requirement. So just to recall what the four requirement is, it has to have fixed number of trials, right? Fixed number of trial, independent, two outcome, and probability of success. So right down here, has to have n trial, and it has to be fixed. You cannot just say that, oh, I'm going to stop now. So independent. So when you are out of those trials, they don't affect each other. And in each trials, you look at two outcome. We label the one that we are counting as success, but it could be anything, as success and failure. And you can determine whatever that you're counting is named as success. The one that you're not counting is failure. And of course, number 4 is the probability of success in one trial. Every trial you will look at, oh, did I get what I'm counting, is equal to P, and it's the same in all trials. Same in the n trial. So this is a very high level kind of description, but you can see that a lot of daily question about asking probability can be modeled by it. So one example would be, I toss a die 10 times and I count the number of 4 that shows up. So we in chapter 3 we learn how to calculate if I toss a die 10 times, what is the possibility of all 4 by looking at probability of 1 4 in one trial is 1/6, right? Because you can have 1 2 3 4 5 6, but this is one of them. All 4, so I mean the first time is 1/6, you get a 4. All 4 of them is all the same, because when you are tossing dice, they don't interfere with each other. So all 1/6 to the 10 to the power 10, right? And it's none of them are 4, that means they're not 4. So for one of them is 5, 6. And if you do 10 times, none of them are 4, so it'll be 5/6. So we learn how to do this in chapter 3. Chapter 3.3, 3.4, multiple steps, right? You just keep on multiplying because they're independent. But we never go into the looking at how do I find the probability of out of 10 times. Sometimes I have 2 4, sometimes I have 3 4s. What is the probability that I have 2 4 but 8 not 4 in 10 toss? So these can be modeled by binomial, and that's why we skip doing that in chapter 3. It's actually exceedingly difficult to write the formula out, so I'm not going to write it. We would just need to recognize that this can be modeled by binomial distribution and use binomial calculator to calculate it. So let's look at this. Do I have 10 n trials? Yes. So these would be done by binomial. Actually, these can be done too, but they're so easy to calculate by hand. So usually, actually all of them can be, but it's just that because I have 10 toss. They're all independent because after I toss 1, the second time I have a 4 is the same. Independent. What am I counting? I'm counting how many 4 I have, right? Success is 4. If I get a 4, that shows up. And failure is not 4. Although you can say, well, I have actually 6 outcome, but whatever that you're counting as success. And then probability of having a 4 in any one time, out of the 10 time is 1/6. The first time is 1/6, the second time is 1/6. So they're all the same. So if you have these 4 requirements, then you can find this probability very quickly, very easily by using a binomial calculator. So in here, because I'm counting 4 as success, so this would be x is equal to 2. You are looking at a discrete probability distribution of x equal to 2. This would be probability of x equal to 3. Right? And you use a binomial calculator to calculate the probability. The second situation would be sampling. So suppose I know that well, actually this is a pretty general known fact that 10% of all adults are left-handed. So 90% of adults, in other words, 90% of adults right-handed. Discounting, there's a small percentage that are neither or both left and right. We just treat it as binary for the time being, right? So if I select 6 adults as a sample, and I assume that independent, right? Because 6 adults out of the whole adult population is less than 5%, so they are independent. I can calculate all these by binomial. Why? Because I am counting how many are left-handed. They are either all right-handed, 0 are left-handed, right? I can count left-handed. 6 are left-handed, x equal to 6. 1 is left-handed, x equal to 1. And x is equal to 2. So x is a discrete random variable. It is binomial. Why? Number 1, what is the fixed number of trial? I have 6 adults, so n is equal to 6. N is fixed. Every time I do it, it is 6 adults that I am doing. Independent because it's less than 5%, even though I am doing independent. Even though I'm doing sampling without replacement, we have 2 outcomes, right? If I don't want to do right-handed, I can say left because I'm counting the left-handed, and the other one I don't have to say right-handed. I can say not left-handed, right? Not. Okay, you can always change multiple outcome. And number 4 would be probability of 1 left-handed, one of them when I pick up 1 is 0.1. It is given 10%. Change it into So they obey these 4 things, and it turns out that there is a formula that can calculate this x equal to 0, 6, 1, 2 in no time. So although they look totally different in terms of the situation, but if they have these general characteristics, they are actually modeled by binomial distribution. Okay, so let's go back to the notes. Figure out if the following x is binomial or not. So x is the number of adults out of 5 who use iPhone. So I am counting the number of adults out of 5 who use iPhone. So do I have a fixed number of trial? Yes. N is equal to 5. Are they independent? I'm only selecting 5 adults out of 5. So it is independent. Independent. Do I have 2 outcomes? Yes. iPhone, not iPhone. 2 outcome. And success is an iPhone, right? So that is success. People that is not using, that is not. And so, and then probability of iPhone, we just don't know, but we know the whole population, there should be a percentage of people that use iPhone. So you can find probability of X number of adults out of 5 who use iPhone by binomial. So this is right. B, number of times a student raises her hand in class. So X is a number. Do I have fixed number of trial? No. No, I don't. I'm counting how he or she raised the hand, but I count until the end of the class. So there is no fixed number of trials, no n. So it's not binomial. This one cannot be modeled by binomial. And then let's do the next one. Make it a little bigger. Get the pen to work. Then I have 3 more. We can discuss if they're binomial. Number of 1 after tossing a die 7 times. Now for this one, I am counting I'm not counting 4, I'm counting 1. And so this is success. 1, if I toss a dice and I get a 1, that is success in one time, okay, in one trial. And then n is 7, right? They are independent. 2 outcome, 1 and not 1. And then probability of getting a 1 is always 1/6, right? So this can be. D, X is the number of tosses until 1 shows up. So I'm counting when I get 1, but I have no n, right? No fixed n. I don't know when I'm going to stop. X is the number of way students commute to school, so either driving or bus or something. X is not even a count, so it's not. So this is also not. Not 2 outcome. So your X is actually not numerical, not 2 count, not 2 outcome. So you should be counting. If you say count how many that take bus or drive, then it is binomial, but not. So if it obey all those 4, then probability of 1, 1, 1, 2, 1, 3, 1, or 1 head, 2 head, 3 head, or 3 right hand, 5 left-handed can be calculated by a formula like this: n factorial over x factorial, n minus x factorial, p to the x, q to the n minus x. Now, what is q? P is the probability of success. P is the probability of success. Q is the probability of failure in one trial. So Q is equal to 1 minus P. So you always just have success and failure. So I'm not going to go into details on how they derive this. And factorial is also I don't know if you know, factorial, n factorial means multiplying something until 1. So you will start with n and then n minus 1 and then multiply until 1. But anyway, this is a formula that will drive you to, if x is 3, then you plug in 3 and then it shows up. But because it's so complicated, we have a lot of binomial calculator that can help us to find p of x. Okay, so statistics can do that. So how do you access it? Maybe I'll talk about this in the next videos on how to find them. But this is a general idea of what is binomial.